Okay, welcome back everybody. Talking about section 8.2 today. We're going to start out with a little warm-up question. It's a review from 8.1's notes. A 3.3 kilogram rectangular air mattress is 2 meters by 0.5 meters by 0.2 meters. What mass can it support in water before sinking? Okay, so basically we're looking at the maximum buoyant force that this air mattress can support. So remember from 8.1 that the buoyant force is equal to the mass of the fluid that is displaced times the acceleration due to gravity. Basically, the weight of the fluid that is displaced. Okay. Also remember that the weight of the fluid displaced is equal to the weight of the object that is displaced. Okay. This is enough information to get us going. It's always, these questions can be a little bit tricky. You're going to always have to remember that you can substitute mass for the density equivalent of it. Okay, recall that density is equal to the mass of the object times the object's volume. So let's go ahead and substitute those into here. The mass of the fluid displaced is equal to the density of the fluid times the volume of the fluid multiplied by acceleration due to gravity. And since we're solving for the largest amount of mass that the object can support, we can go ahead and leave this side like that. We're going to go mass that we're trying to solve for plus the mass of the air mattress, which is given to us in the problem, times acceleration due to gravity. Now it's pretty simple, just plugging in the values that we know. Remember that the density of water is 1,000 kilograms per meter cubed. The volume, we simply have to find that. So volume is going to be 2 meters times 0.5 meters times 0.2 meters. So our volume is 0.2 meters cubed. And if you notice, acceleration due to gravity is on both sides of this equation, so those are going to cancel out. We don't have to worry about that. So then we're left with mass plus the mass of the air mattress, which is given as 3.3 kilograms. Solve for the m there, and you're left with 196.7 kilograms. Okay. Remembering this right here is important. That's probably something you should have on your note card. It's a good thing to remember. Okay, moving on. Section 8.2 is about fluid pressure. Okay, two things we're going to make sure we understand after today is we should be able to calculate the pressure exerted by a fluid, and we're not going to calculate this, but we need to understand how pressure varies with depth. Okay, pressure, we've all felt pressure before. When we're talking about pressure in physics, we're not talking about pure pressure. Okay, we're not talking about pressure that you feel when you're stressed out. All right, we're talking more about this other type of pressure. The pressure you feel when you get a shot, the pressure that this guy is feeling when he gets punched in the face. Okay, pressure is really affected by two things, and that's the amount of force that is applied and the area that the force is applied to. Okay, now this gentleman that got punched in the face here didn't have the other guy's hand go through his skin. Yet this needle, which I'm sure was not pushed in with as much force as that punch, went all the way through the skin. Okay, now our equation, oh, it's also why this person can lay on a bed of nails and not get skewered. Okay, and I'll explain that here. Because the equation for pressure is pressure, which is another P, is equal to force divided by area. Okay, force divided by area. Okay, so the greater the force, like the punch, okay, there's a great force applied here from the punch over a larger area. But in the needle, there's a smaller force, but a very small area that is applied over. That's why in this example, each individual point of the nail that this guy is laying on is distributed. The guy's weight is distributed more evenly, so he's not stabbed, which is good. So pressure is equal to force over area. Our units for pressure are the Newton over meter squared, which is equal to a PA, which is known as a Pascal. Okay, PA is a Pascal. And which leads us right to Pascal's principle. Pascal's principle is, it states that the pressure applied to a fluid in a closed container is transmitted equally to every point within the container. We'll get to that in just a second. Now, just to put some reference points for you here, a Pascal is actually a really small unit of pressure. There's another unit of pressure called an atmosphere. Okay, it takes it's 1 times 10 to the 5th pascals is equal to 1 atmosphere. Okay, that's a good thing to remember. An atmosphere is measured at sea level. So if you were standing on the beach at the ocean, that's the amount of air pressure that you feel. Okay, so that's 1 times 10 to the 5th pascals. Okay, so a Pascal is actually a pretty small unit of pressure. All right, on to Pascal's principle. Again, it says that pressure is exerted equally all over a fluid container. All right, so in our example right here, if you have water in a container, it's exerting pressure equally out on all sides. Okay, that's what the arrows are indicating. That is why balloons work. Okay, a balloon is usually, it takes the shape of the balloon, but the air in there, which is a fluid, is exerting a pressure equally out on every side. That's why you don't end up with like a lump on one side of the balloon or something like that. Okay, it's also how hydraulic lifts work. Okay, anything that works on hydraulics is based off of Pascal's principle. That's how you're able to apply a small force to move a very large object, like in this example on the bottom. Okay, you apply a smaller force here, and because the pressure is the same all the way throughout this hydraulic chamber, it's going to magnify the force on the other end. Okay, that's how you're able to lift a car with your hydraulic jack. There's a very simple ratio that we can use to figure this out. All right, it just takes our pressure equation and puts it into a ratio. So the force on this first side divided by the area of the first side is equal to the force exerted on the other side divided by the area on the other side. Okay, it's a simple ratio that we can use. Got a little practice problem to go along with that. The small piston of a hydraulic lift has an area of 0.2 meters squared. A car weighing 12,000 newtons is on the large piston, which has an area of 0.9 meters squared. How large must the force on the small piston be to support the car? All right, so we're looking for the area. Let's write down the stuff that we know. We know area 1 is equal to 0.2 meters. We know that area 2 is equal to 0.9 meters. Oh, squared. Don't forget to square that. It's area. Okay, now the forces. This can be a little bit confusing. The car has a weight of 12,000 newtons. So that is actually going to be force number 2. Remember, weight is a force. That's why it's in newtons. So force 2 is equal to 12,000 newtons. Force 1 is what we're looking for. We want to find out how much force you need to apply to lift that car. So we just plug this into our ratio, make sure the ones match up, and make sure the 2's match up when you line them up in your ratio. That's going to be the only tricky part with this. So force 1 is what we're looking for, over area 1 is equal to force 2 over area 2. Plug in the values we know. Force 1 is the unknown variable. Area 2 is 0.2 meters squared. Force 2 is the weight of the car. Again, you know it's a force because it's in newtons. And area 2 is 0.9 meters squared. Solve all that for F1, and you end up with 2,700 newtons, which is not a great deal of force in comparison to the very large force of the car that you're lifting. Okay. Again, that's all based off of the idea that inside of this closed container, pressure is equally exerted on it. All right, that's why a pop bottle has, if you shake it up, it feels firm on all sides of it. Okay, it's not hard on the bottom or hard on the top. It's firm everywhere because the pressure inside of it is exerting equal pressure all over the place. Okay, now the last thing we're going to talk about just real quickly is how pressure increases as depth increases. Okay, this is why if you go swimming and you go to the bottom of the lake or you go to the bottom of the pool, you feel that pressure on your ears. Okay, it's the same reason why if you go if you take a plane flight, the higher up in altitude you go, you feel your ears have to pop. Okay, the higher you go, the less pressure you feel. So your ears are at a difference in pressure. When you go deeper into the water, you feel more pressure. So there's a difference in pressure. That's why your ears feel like they need to pop. Okay, that's why in this example right here, okay, you can see this cup has holes put in it at different depths. And the further down you go, there's more pressure, which is why these are shooting out further down here than these ones up here. Okay, again, more pressure at the bottom. You can think of it like this. The deeper you go, the more stuff is above you. Okay, you can think about yourself walking around all the time with a giant tube above you. If you are higher up in the tube, say you climb a really high mountain or you go in an airplane and you go higher into the atmosphere, there's less air above you pushing down. You feel less pressure. But if you're at sea level, you feel greater pressure. All right, if you go deeper into the water, the deeper you go, the more water is above you pushing down on you. So that is why pressure increases as depth increases. Okay. That should be all that there is for today. Also, on your worksheet, it asks you to go to the animations and simulations. There is a similar animation and simulation on the section 8.2 here. You just go to the website, go right here, and check that out on Pascal's principle right there. Again, if you have any questions, please let me know so we can get them answered in class. Section 8.2 assignment will be due on Tuesday. Thank you.